Sure. Okay. So yeah, excited to be here. Nice to meet you all. I'm Albert. Me and Karan did our PhDs at Stanford over the last few years, and started working on some of these state-space models. I spent a bit of time in industry as well at DeepMind, and then went to CMU, where I started this year as an assistant professor in the machine learning department, and continuing to work on some of these ideas around alternate models, fast inference, and so on. We also started a company this year, so Karan will probably say a little bit more about that, where we're using these models. So we'll talk a little bit about that as well, and kind of show some more fun applications of some of these state-space models, so you can see where we're going. And then I'll talk a little bit more about some of the technical stuff. Yeah, this is well, why don't you introduce yourself?
Yeah, and then I want you to respond to the comment in a second.
Oh yeah.
Hey, I'm Karan. I'm the co-founder of Cartesia and CEO. And before this, I was doing my PhD. I was a couple of years junior to Albert at Stanford, and we worked together a lot on state-space models. And then the other half of my PhD was kind of focused on a mix of robust machine learning, and some work on data systems, evals, etc. I also worked on a bunch of things across the board. I did my master's CMU, did my undergrad back home in India, and then now really excited about applying SSMs to build real-time models at Cartesia. And Cartesia has been around like 8 or 9 months, and we'll talk a little bit about kind of what some of the work we're doing there.
Awesome. Guys, by the way, throughout the talk, people can just raise hands and then I can curate. You don't have to keep an eye out for the chat. I'll just interrupt you myself, and then if that's fine with you, of course. Hey guys, I want to give a huge shout out to Hyperstack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing. Basically 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick the environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select the environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s, you select the images, you select the SSH key you just created, and hit deploy. That's it. Literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough, honestly. The thing they kind of focus on is basically, because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're an individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
So why don't you?
I can get us started, and then you can take over. Yeah. So we started Cartesia a few months ago. I think the main sort of reason behind the company is that a lot of the foundation models that are being built today are kind of really kind of focused on batch workloads. So the idea is that you're running a fairly large model in the cloud. Very slowly. The model is very intelligent, but takes a lot of time and is very compute intensive to run. There are a lot of applications where what you need is actually interactive models. You need to be able to have the model return and process kind of inputs very, very quickly. And so what you would like is that these models are more real time. They're faster, they're cheaper to run because you're kind of running them constantly. And then they're more close to on-device edge sort of sensors and applications so that you can actually kind of deploy them wherever the data lives. So that's kind of I would say the 2, sort of dividing the world of models into kind of 2 big buckets, batch-oriented and kind of streaming-oriented models and workloads. And so really why we started the company was we really wanted to focus on the second bucket, which is real-time streaming intelligence, which is typically much more focused on sensor data, audio, video, etc. And I think part of the reason why this is super exciting is because real-time intelligence is very useful. There are a lot of different applications that rely on the ability to understand or generate in real time. So some examples of this include assistance on device, being able to converse with a computer very easily and quickly, doing generation for things like gaming or VR, where you're trying to render frames or audio in real time. And then even think about AI on any device, like a robot or a car, any place where you're really trying to kind of have a device that you're interacting with. And so I think what's really interesting is right now, a lot of the really intelligent models are constrained to the data center, and how do we kind of bring them closer to these sort of device surface areas, and what kind of models do you need to get there is sort of the real question. And so at Cartesia, we're building these real-time foundation models. So we worked a lot on the foundations of sort of efficient long context real-time models with SSMs, which is the work that Albert led at Stanford during his PhD. And we really kind of started the company to focus on this set of questions, really kind of try to develop new technology that would allow us to build really fast, cheap, high quality models. And then at Cartesia, we're basically building this team that will go build these models, and we'll show you a demo of sort of a first model that we released like 10 days ago. But there's a lot of exciting work we're doing around this that we'll continue to do over the next few months and years. One thing I want to highlight, is that it's still pretty challenging to do AI. Like, I think a lot of folks have been really excited about the progress that's been made, and rightly so. But also that, I think when you compare to humans, we are very good at processing multimodal, multiple signals very, very fast. And so one example of this, which I did a calculation off the back of the envelope, is in about a year, humans are understanding and remembering information on the order of like 1 billion text tokens, 10 billion audio tokens, and 1 trillion video tokens. And this is probably a conservative estimate given the resolution of the data that we look at, and how much processing we do, including proprioception, et cetera. So I think that there's still a very long way to go to be able to do all of this computation very, very quickly at low latency on fairly constrained compute. And so I think going from 10 million tokens in a data center into something like this is still a fairly hard journey and requires a lot of innovation to happen. And that's kind of what we're excited to do. Before we dive
question here.
Sorry, I'll stop here.
Just a quick question. When you say the best models today can only process 10 million tokens in a data center, what do you mean by that precisely? Like in the sense of in a single go, in a single context window, or?
Yeah, I think I was mainly referring to context windows of the most intelligent models. Their ability to kind of keep all of the information around and model kind of long-range dependencies in the data. You might be able to remember. I certainly remember I got married in December. I was there. I certainly remember most parts of the wedding. Maybe some parts are a little bit missing for understandable reasons. But I think the fact that I can recall all this information and then be able to tell you maybe a story about it is kind of evidence that I have a much more clear understanding of much more historical data than any of these models are able to do. So that was about 6 months ago. Let's say that's 500 billion tokens ago for me, and that's not something you would be able to do very easily.
Yeah, and that was a lot of the motivation of the original, like the S4 and Mamba lines of work came from a lot of technical stuff where it really wasn't inspired by this idea that the brain kind of does this fuzzy compression. It's like a fixed size kind of state in a sense that's doing a fuzzy compression of like lots and lots of context, the whole lifetime of context. And that idea of how can you do kind of like continual lifelong learning and really handle basically unbounded context windows. Of course, there's going to be some sort of compression and fuzzy recall there, but that was kind of like definitely an inspiration for a lot of these, the technical side of the models. Yeah.
Makes sense. Super cool.
We can probably skip this and
yeah. Do you want me to show the demo before?
Yeah. Why don't we do that?
Yeah. Super quick.
Yeah. So I think
is that the one for text to audio, like the one you?
Yes.
Yeah.
Yeah.
I don't know if you've seen this. And just before we get into,
Chrome tab.
oh, sorry.
Yeah.
Can you see this?
Yeah.
I mean, I actually haven't even played with this.
Yeah,
You can go.
you can see it.
So yeah, I think this is a playground that we put up for a voice generation or text-to-speech model that we have been building. These models are some of the first to be pushed to production that really are built around SSMs, and so kind of the first kind of proof of concepts of this technology working in practice. I'll show you a couple of quick demos here, and then we can dive into kind of the background. But
I can also share the link for folks so they can check
yeah,
it
you
out
can
later.
share. I mean, let me do the tab audio super quick, and then you can share the link.
Prepare to embark on a journey where intellect reigns supreme and victory is but a well-executed maneuver away.
So this model, I think one of the cool things about it is just that we were able to bring down the latency to something that's really, really low. And we're continuing to kind of optimize these models. But the idea is that it's very much in line with this idea that you need real-time models. You press the button and audio streams out. And you can imagine kind of the same thing happening for things like video or other modalities that in the future where you kind of can instantly generate a very high-res data very quickly. And so this is sort of the first kind of demonstration of this tech really working. We can share the link. I encourage folks to play with it and just reach out to us if you think something's broken or interesting. We always love to hear feedback.
Okay, cool.
Awesome.
So let me
I
get
actually
back to
did hear it the last time you played it out, so I hope
that.
that others
Okay,
heard it as well.
that's fine. Yeah, I would just like starting with kind of more of an application because I don't have much in the technical slides. I don't have much in the way of results here for a while. Okay, can we see this again?
Yep.
Sharing this. Okay, awesome. So cool. So let's kind of so now I guess we can talk about a lot of the details of these models. And so this can go many ways because again, this is like years of work to build up to this, and I'm gonna kind of give like a high-level summary of some of the different flavors and the progress that's been made here. But I'm happy to dive into any particular facet of these. So broadly speaking, the state space models are they're actually, I think they have kind of a reputation of being complicated, but actually the model itself is quite simple in terms of its definition. Yet it has a lot of really interesting properties, and that's kind of one thing that's super nice and compelling about them, and why they kind of feel fundamental. And in fact, like they're so fundamental that lots of other fields have basically encountered similar versions of these. And so they're a really rich area of subject. But at the end of the day, the way we can actually use them in deep learning is pretty, it's actually pretty straightforward and not too complicated. The model itself is kind of defined by these equations here. So it's basically defined by there's a differential equation that kind of governs some recurrent or continuous dynamics, and then combined with a projection thing. So I'll explain these equations in a little more detail in a second. By the way, are there like pointers here? Can you see my mouse?
Yeah, we can.
And this exact formulation of the model was actually first described by Kalman in many decades ago in the context of control theory. And like the Kalman filter is still something that's used these days. So they're fundamental. They've been around a long time. And many flavors of them are still around. And so people also think that these like the form of SSMs or state space models that we use in deep learning now are very related to this. But actually they differ in many kind of important distinctions, subtleties. And so I actually think of them as not quite related to kind of the flavor of these models that have appeared in statistics and engineering and these other fields. And there's a more technical sense in which I think of them as really like pure deep learning models. So we'll talk a bit about kind of those distinctions. But these models basically, so what I call structured state space models is kind of this is what I more specifically refer to as a particular deep learning model that is basically kind of like, you can think of it as a layer that can be used in neural networks, just like an RNN layer or a transformer layer or an attention layer. And this layer has a lot of really nice properties. And they're broadly related to lots of other types of models, including the classical state space models from like statistics, engineering controls. They're also very closely related to other things from modern machine learning and deep learning, such as recurrent neural networks and convolutional neural networks. And if we get to it, we'll also see that they also have connections to attention as well. So really, I kind of think of it as this I think of it as like this primitive layer, like a black box that you insert into your neural network that just has a lot of it's like a very deep thing that has a lot of connections to all sorts of other models. So the kind of the first version of this is, so this whole flavor of model is what I call a structured state space model. And maybe I'll say a little bit about why that name. But we usually, like when people talk about SSMs in deep learning nowadays, they refer to this flavor of things, which is not quite the same as like other forms of, people will sometimes get confused, like people from the controls community or whatnot will get confused because they think that we're referring to things like the Kalman filter, but those are actually like, they are related, but they're actually like quite different in many important ways. So, and so these models kind of, they have all these connections. And so we like to use this diagram to kind of depict some of the most important properties and connections of these models. And so I can talk about them, kind of go into a little more detail about some of these. So one thing, so the first kind of way to think about this model is that in neural networks, basically we, if you think of what an attention layer or a CNN layer or like a convolution layer or an RNN layer does, you can basically think of them as parameterized functions that take an input sequence to an output sequence. And so basically, if you think of what goes into your transformer, you basically pass it in a sequence of a certain size. So there might be like a mini batch dimension, and there might be like an extra channel dimension. But basically, you pass in a bunch of sequences, and then you can think of your attention layer as just this black box that returns an output sequence that's kind of the exact same shape as the input. And so basically, this is the first sense in which these models are, what I mean by a sequence model is that they have the same interface. And we're going to think of them as something with some parameters. In particular here, the parameters are going to be these ABCD things that I highlighted here. And so those will be learnable parameters. But what do those parameters do? They basically define a map from an input sequence to an output sequence. So this already is a little bit subtly different than the way that classical state space models were thought about. In like control state space models, you actually kind of, they share the same equations, but you think about what are the parameters, what are the inputs and outputs, or like what are the things you control, what are the things you're given in a different way. So here we are putting our deep learning hats on, and this is the way you think about the model. It's just a map from a sequence to a sequence. Now, SSMs are already a little bit different from your classical sequence models, like, sorry, your like deep learning sequence models like attention and so on, because the input to this model can really be thought of as a function that's continuous over time. So, and that's because if you remember the equation, there's this differential equation in there. So you basically think of it as like, instead of a discrete sequence of points as the input, you could think of it as a continuous function. And then your model would be able to process that and return an output function. Now, this is a little more powerful than a sequence-to-sequence map because you can always just sample these functions and recover a sequence-to-sequence map. Okay, and so we're going to think of it basically as this map from a sequence to a sequence. How does this map work? That's where the state part of the state space model comes from. So we're going to think of the first equation as taking the input sequence and converting it into this higher dimensional latent state. So that's depicted in blue here. So again, we're thinking of the whole thing as a map from this input to the output, this black line to the red line. And then the first equation is going to turn the input into this this state. So you can basically cover up the top and think of like hitting the inputting this differential equation with your sequence here, and then you can have a unique solution from this equation that determines kind of a higher dimensional state. You can think of this A matrix as this transition matrix that's kind of governing how the state evolves through time. So the differential equation part is like might look a little bit scary, but you can really just think of this as kind of like you can think of it as a recurrence, which we'll see in a second. But you can basically think of this as kind of like similar to a very simple form of a linear recurrence where you take your input. So at every time step you take, like you hit it with a new input. You process this input kind of into the same dimension as the state, and then you evolve the state by a little bit, and then that gives you the new state. So this equation kind of tells you like how is your state changing over time, and it's very similar to any other type of or kind of like a special type of RNN where yeah, you're basically just evolving your state through time. And so that's going to define.
So sorry for interrupting. Yeah. So in this particular example, you're mapping what 1D function to a 4D represented by the 4 blue curves, and then you go back to the original dimensionality in the output space.
Yes, that's exactly right. So, yeah, so you can think of this B as kind of a 4x1 column vector that takes your one-dimensional input, blows it up to 4 dimensions, and then those 4 dimensions are the size of your hidden state that kind of evolves through time. And this first equation will determine how your blue state evolves as your input, as you're getting new inputs. And then the second equation is going to take your state back to the output space with basically a simple linear projection. So here there's no differential equation. It's basically a position-wise or point-wise linear projection. So this equation is quite simple. So that's exactly right. And now I guess one thing to note is that the dimensionality of this hidden state is going to be bigger than the input space. And that's kind of one facet where this kind of differs than how people usually thought about RNNs. So there's two particular ways in which this kind of differs from RNNs. Maybe we should talk about this in a second because I'm going to talk a little bit more about the recurrence point of view. But one very important characteristic of this model is that you are getting a larger hidden state. And so you can think of this hidden state as kind of something that is summarizing your information at any given point in time. And so you want like a state that's large enough to kind of remember stuff in the past. So this will be a theme that keeps coming up. So this slide was really just to kind of illustrate what these two equations are doing. And so basically, you can just drop these into any neural network. You can parameterize the A, B, C, D things as parameters, and so you can learn them with, and then these parameters will determine a map from X to Y. And then you can basically learn everything end to end using gradient descent, just like any other neural network layer.
Is this, strictly speaking, more general than a transformer in the sense that you can represent the transformer by a specific instantiation of these formulas here, or?
So this is a great question, and I'm also going to touch on this a little bit later. So I would say that this doesn't exactly represent the transformer, like the softmax attention as we know it. However, there's kind of a way to view transformers as, in some sense, they are a form of state space model in the sense that there is a state to the model. However, the form of that, the whole question is, how does a model define its state and how does it use its state? Now, what characterizes these models is that the state is this kind of like, in here, it's a 4-dimensional thing. In general, maybe you can think of it as like a 100-dimensional thing is the typical dimensions that we'll use. And the question is basically, what does that state represent and how is that changing through time? And so the way that this state, we interpret the state in an SSM is different than the way you interpret the state in a transformer. So that's actually going to happen. I'll talk about it a little more in a few slides, but that kind of connection is actually a very important theme of some of the follow-up like that's more closely related to the inspiration for Mamba, which is going to kind of follow up on all of this right here.
Perfect.
But yeah, that's a great question. So let me just keep moving. So this slide basically is just trying to illustrate the definition of the model. And so again, like it's really, you know, just two equations. They both are interpretable and not really that complicated if you actually unpack it. Now, the first property that I mentioned in these three little depictions here is basically that unlike things like transformers, these models connect to other types of sequence models that might want to operate in continuous time, such as you can think of it as a form of neuro ODE, even if you've heard of those. And so these can process kind of natively continuous input. And for example, we did a bunch of work showing that it's really good for working on things like audio signals. And that's kind of one reason why one of our first demos was related to audio at Cartesia, but basically because types of modalities that are really smooth, actually like transformers don't handle those well. And the original type of SSM that we were working on handles those really well. And it can do interesting things like automatically adapt to different resolutions and stuff because of this connection to continuous models. Now, the second point of view of them is basically what we were just talking about, which is kind of as an RNN. And so basically one way that you can actually think about computing this model in practice is that you think of this differential equation again as like, there's a very simple way to convert it into like a discrete time recurrence. And then you basically just think of this as like a linear RNN where you kind of see inputs online, and then you feed it into the model, you use this equation to update your state, and then you project it back out. So the advantage of this and the advantage of RNNs in general over things like transformers is that they have this kind of like finite size state that can be updated really fast. So that's basically the one way to compute the model, and one reason why there's a big advantage here, especially if you think of like a language model, and you, of course, transformers are the most popular there, but if you use a state space model, the advantage is that when you're generating new input, or when you're generating new outputs as a completion of your autoregressive language model, the way you do that is you kind of unroll it one step at a time. You produce one output and you feed it back in, right? You produce one token, feed it back in. You only see one token at a time. And so that's the problem of autoregressive inference, is one word for it. And that's a huge advantage of state space models because they have this finite state that can be unrolled really fast. And so this is in direct contrast to other types of models that might have much larger states. And so and again, this relates to your question just now, Aleksa, and I'll talk about that a little more a bit later. Now, one more thing kind of from a theoretical perspective of this is that what makes these models interesting to analyze is that because you only have kind of a finite state that we are evolving, a big question becomes, what does that state represent? How do you get that state to remember the relevant parts of the data that you're seeing? And so that is that actually can be quite involved to kind of figure out how to design your state in a way that's encoding the information you want. And so that's where a lot of the initial kind of technical theory behind these models was focused on. Yeah, so that's kind of one of the main considerations of this recurrent representation is what is the state? You think of this state as kind of evolving through time, summarizing what you've seen so far, and that's something we have to analyze. But the advantage is that it becomes really fast if you're seeing inputs in an online or autoregressive fashion. So as an example of some of the initial theory that went behind these models, so we kind of we did a bunch of work to try to design autoregressive state space models where the state is encoding something very, very specific. And so the intuition behind these models, again, is that you can evolve them through time. At any given point, the state is a compressed summary of everything that you've seen so far. So this is very directly analogous to kind of what Karan was saying about the way the brain is kind of fuzzily remembering things from the past. Right. So and so how can we define what it means to remember or like fuzzily compress things from the past? Well, we set up this technical problem where we said, let's design a state space model such that at any given point, the state in blue, which is a fixed size vector, can be used to try to attempt to reconstruct the data that we've seen, so far. So here, what's being visualized is that we had the exact same input sequence as before. Now we're kind of saying we're observing them in real time, and our state is evolving through time. And now I'm gonna, with just a simple linear projection, how close can I reconstruct the entire history of the inputs that I've seen? Now, of course, this problem is not well formed in the sense that you can't perfectly reconstruct everything. So we're purposely doing like fuzzy compression here. But that's kind of exactly the way that many like biological agents work, right? And so what we're seeing is that the reconstruction is not perfect, but it's doing kind of this approximation. And it's more accurate towards kind of the current time point, and then it kind of degrades farther out, which is probably an intuitive way to think about these, what your state would encode. And so this was kind of the predecessor to S4 directly, and which was the predecessor of Mamba. Now, it sounds like some of the audience members are quite familiar with some of this literature, and so early on we got kind of a question or comment about this other model called an LMU, and so that was the predecessor to Hippo, which kind of introduced this one particular instance. So Hippo was like this broad mathematical framework. There was a previous model that kind of that first introduced the first version of it, which was like one instantiation of this, so that was actually inspired directly by kind of these techniques from computational neuroscience, where they were analyzing state space models in a different context. And so, yeah, so this is kind of an example of how these various forms of SSMs have been around for a long time, and they've kind of continually evolved. This Hippo and the previous, the Lejeune memory unit, which was mentioned, were very much more like theoretical things that were trying to encode certain things. Now we've kind of moved on to more of a deep learning interpretation, which is what I was explaining before, where we just think of these models as kind of being these black box sequence-to-sequence maps. We actually were able to kind of drop a lot of this theory, which was a little bit intimidating, to be honest. It was very nice, but it turns out to not really be necessary. So you don't really need to think about these, but there are kind of a lot of interesting theoretical connections.
Just a couple of questions on my side. You mentioned this decay window on the previous slide. Like,
yes.
How do you specify it, and what's the bias? How do you build in that bias that you just mentioned, that further away steps should be less remembered? What's the logic there?
Yeah. So I'm gonna head out. I have to run, unfortunately, for another meeting, but Albert will be here, and ask him hard questions, please.
All right.
Perfect.
Yeah, so yes, that's an excellent question. So basically, on this particular animation, I also have depicted in this green line here, is what we call the kind of the weight function, or the measure, which specifies how much do you care about various points in the past. So I mentioned kind of this particular one is this thing where the red reconstruction is like accurate at the current time step and kind of decays further out, and that's reflected by this green line, which says this is how much I care about various points in the past. Now this green, what we call the measure, is it's a flexible thing that you can specify kind of as a prior. So there's so like I said, Hippo is basically more of a general framework, and you can instantiate it in different ways using different forms of this measure that try to encode different kind of inductive biases or priors on what I want to remember.
Do you typically learn it, or is it just specified ahead of time?
So these particular things, the very first version we specified ahead of time. You can essentially interpret. So one way to kind of interpret that is that that prior is baked in. Essentially, it's just going to be baked into the recurrent dynamics of the SSM. So it turns out, like, after you go through the whole framework of Hippo, what you end up getting out is that the measure that you've specified can be converted into like special formulas for A and B. And so it basically says that like there is one particular state space model that is encoding that particular prior on what it's remembering, right? So the idea was that like this first equation is the thing that that controls how the state evolves. And so naturally, if we want the state to encode a certain thing, then it's basically going to be encoded into like represented by these recurrent dynamics, the A and the Bs. Now that means that you could almost interpret the version of this where, so the first version of this, we didn't even learn these. And like I said, it's evolved more and more towards this like standard deep learning interpretation, where now we can learn these A's and with the A and the B. And when you learn this, you can almost think of that as being the thing that is learning this kind of this measure. So we're not going to learn the measure like directly, but we are learning the SSM dynamics, which you can basically think of as a proxy for this. So again, there's like a lot of like interesting theory here, but for the most part, I mean, of course, like I think it's really interesting, and this is what led to this. But you don't really need to think about it anymore, especially for the practitioner. And that's kind of a reason why it's like we are now just basically going to learn everything, and in some cases, like you can basically think of it as exactly doing a sort of really interesting like memorization according to some mathematical principles. But now we can basically just learn them. And to be honest, like there's a lot of, I think, interesting interpretability work that could be done, which is like, let's look at a trained SSM and look at what its state is encoding. Can we back out what sort of information has it encoded and what dynamics has it learned and stuff? I personally have not done a lot of that work because I work more on kind of capabilities research most of the time. I have intuition for what it's doing, but I haven't done the actual probing myself, and that would be a very interesting area of future research.
Mm-hmm. Maybe one more question on my side is, what's the main computational property of SSMs compared to a transformer? Because obviously that's something you stressed in the beginning of making real-time intelligence as opposed to batch.
Yeah, that's right. That's right. So, great question. So that's kind of one of the points of this, which is that the recurrent point of view basically says that for every single new input I see, I can process it in constant time, like a fixed amount of time, the same amount of time, no matter how many, for every input I see. And so this is also like a huge advantage of these recurrent or stateful models over things like a transformer, where I have some more slides later that kind of contrast them, but you can think of a transformer more as doing this like cache of your whole history, like an exact memory store, an exact cache, or like an exact database of every single token you've seen in the past. And that works very differently than the way like human intelligence operates, right? So so again, we kind of see this analogy again, where we kind of think of SSMs as this thing that is a little more analogous to like a real-time intelligence system, like a brain, where you know, like any new data you process, I mean, if you're constantly processing information and processing it instantly, it's doesn't necessarily scale with kind of like, yeah, it's not going to slow down, you know, as the longer you live. That's, you know, a very crude analogy, but that's kind of like one of the main advantages of these models from a inference perspective. How fast can you process new things? So that's kind of why these applications that potentially involve real-time streaming, like the audio thing we just saw, these are some of the most directly maybe like applicable or interesting applications of some of these models.
Doesn't that imply, like, if you're getting obviously much better inference in the sense that you don't scale quadratically, you can just like do constant time, as you said, doesn't that imply that you have to sacrifice flexibility? Like, it feels like there should be no free lunch. And I think I saw some of the recent papers where he actually showed even better perplexity and then combined with better inference properties. Like, what's the trick? Where is the catch with the models? I'm still learning about them, so sorry about that.
Yeah, no, these are perfect. These are very insightful questions. So exactly, there is no free lunch. So basically the catch is that, like, as you can see here, like these are all fuzzy compression, right? So they have a lot of advantages, because another way you can think of it is that it's like stripping out complexity from, it's like stripping out unnecessary information. So you can think of like compression is good a lot of the times. And that's one of the disadvantages of transformers, is that there's no need to remember like every single token you've seen. What if some of those tokens are useless? And so compression is useful. Fuzzy compression is probably, actually, I think, is probably fundamental to intelligence. However, by definition, it can't do some things that there's things it can't do. And for example, one thing that transformers do really well that SSMs don't do well is like exact lookup, exact retrieval. And so people have designed kind of synthetic tasks like phone book lookup, which is like give the model like a giant phone book, and then give it a name at inference time to prompt it with and ask it to retrieve the corresponding phone number. This is something that because these models are doing fuzzy compression into a finite state, they can't like exactly remember everything in the past. Now, the question I have that's kind of more philosophical is that a feature or a bug? And I mean, in the sense that human brains can't do that either, right? And so people think that SSMs might be kind of a more biologically plausible solution that's actually the bulk of the processing power, and it can be augmented by things that can do exact lookup and exact retrieval, which is something that attention is very good at. And so that's why we're seeing that some of the best models nowadays are basically these hybrid models. And I think by now, many independent groups have sort of come to the conclusion that some sort of hybrid model that involves mostly SSMs and a little bit of attention, maybe like 10%, seems to be the sweet spot that does the best on, that can do like all of these different capabilities and has the best perplexity and kind of just gets the best of both worlds. And so hopefully that intuition is sort of makes sense. Actually, let me, you're asking really great questions that I think will actually be a little more appropriate for the slide in like 3 more slides. So let me just finish talking about the original formulation of these models are actually a little bit different than the Mamba formulation. So we're still kind of on like the S4 formulation. And the last thing I was going to say is that there's this final property depicted here, which is that this model I mentioned is also related to CNNs. I'm not going to go into the math, but basically, remember that the whole model was a map. You think of it as a map from an input sequence to an output sequence. We thought about it as going through this latent state, which I was in blue here. There's a second way of thinking about it, which is that you can also represent it as a convolution. And remember that a convolution is something where you have like one convolution filter, which is depicted in green here. You kind of slide it along and take a dot product at every position. It's just the standard definition of a convolution. And so another thing that was very interesting is that these in some ways generalize or are very related to CNNs. Now, Mamba is not related to CNNs, and I'm not going to go into all the details there, but the point here is more that you have all these very rich connections from to recurrence, to like these continuous time systems, to convolutions, and all of them are useful in some ways. And so different flavors of SSMs can solve like many different problems because they kind of are so fundamental and broadly related to all of these things. I don't want to say too much about this because I think I want to talk a little bit more about Mamba, which is the motivation of that was kind of more of the questions that you're asking, Aleksa. And so basically the kind of the key thing to think about in terms of how do these models work on language modeling is basically the question of like, what is the state? And so we've already kind of touched on this, but basically one way that you can think of all of these models, including transformers, including SSMs, if you think about the way they work in, say, language modeling, like autoregressive language modeling, all of them have some notion of a state, which is simply like, what does the model have to remember in between time steps? If you have a GPT model that's generating stuff, in between every single new token that it generates, there is some state that it has that's evolving. And the question is, what is that state, and how does it? What are the trade-offs of that state? And so, kind of like the point that we were kind of talking about with RNNs and SSMs is that, so here's kind of like an old school RNN, more like an LSTM. But the point is that this is a model that has a fixed size state, similar to SSMs. And that state is some summary of everything the model has seen before. It's doing some strong compression. And why that is both good and bad. It's good because it makes the model much faster during inference. It's bad because that state cannot remember everything the model has seen. So that's exactly what we sort of just talked about. If you need to do like exact retrieval, phone book lookup, your finite size state in our current model can't do that. However, but like as I kind of mentioned, you probably don't actually want to do that most of the time. Like compression is actually a very powerful kind of a tool toward intelligence, because it also means that you are trying to remember exactly only the most important things into your state, and you kind of strip out the rest. And now you can augment this with something like attention, which we think of as the exact opposite of the spectrum, where the state of a attention model or a transformer is basically a cache of the entire history that's doing no compression. So if you're familiar with this concept of a KV cache, basically the way you do inference with attention is that you literally store kind of this, you literally cache a token of every single past, you cache every single past token that you've seen. And you basically just like write it down. You can think of it as like a, like a memory bank that you're just memorizing it. And so this also kind of characterizes the trade-offs of attention. This is why it works really well, especially on things that require like a lot of precision about something that's happened in the past. However, that's also why it has this kind of famous quadratic bottleneck problem, which is, you can think of it exactly as a consequence of the fact that it is like, it's a retrieval model that's doing no compression, is why it's quadratic time. And so that's kind of just like a very kind of a high level, but I think insightful way to think of the trade-offs of these types of models, between attention, which does no state compression, and SSMs and RNNs, which have a strong state compression. And so, like I said, I think kind of combining these two into hybrid models is something that people have found makes a lot of sense. And again, we can draw the analogy to, say, biological intelligence, like with humans. It seems a little more intuitive to me that we're closer to SSMs. We do fuzzy recall and compression of the past. But if you augment a human with like, that's why if you have like scratch pads taking notes, or like being able to look things up directly from the dictionary, from a book and so on, that's kind of like what the attention is doing. It's augmenting you with this ability to look up exact stuff kind of from an external source of information. And that kind of combination is very powerful and kind of augments your intelligence, while still getting most of the benefits of kind of the very fast processing of these state space models.
Just quickly on the efficiency bit, like how much can SSMs benefit from the existing infrastructure that's been developed for transformers, in the sense, for example, a good proxy would be what's the MFU when you're training some of these models? How much can you squeeze out the GPU when training them?
Yeah, that's another great question. So, so one thing that has been, I can say, like, one thing that's been a little bit difficult about like alternative models to transformers is that, have you heard of this concept called the hardware lottery, which is kind of this idea that hardware and models and software kind of evolve in this feedback loop, and that's it's good because you can really squeeze out you can maximize certain types of models. It can be negative because it kind of makes it harder for other types of models to realize their potential benefits. So the original formulations of these models had a lot of work went into making them like reasonably efficient on GPUs, and so these models like S4 and like Mamba were all quite efficient, like pretty reasonably efficient on GPUs, especially compared to like older models like LSTMs and so on. So that's a lot of the stuff that I work on in my PhD, as well as people like TreeDAO, who we were in the same lab and we worked together a lot. However, even so, it's not quite as efficient as attention, which is just, attention is just doing these like very coarse-grained like matrix multiplications. And then the hardware started being more and more optimized toward matrix multiplications. And of course, then transformers got faster and faster. That's kind of like one potential downside. Now, I don't think that's fundamental because, again, it's more of an artifact of how things have evolved based on this feedback loop. And now that we've hopefully kind of shown that there's a lot of advantages to other models, that can start like a feedback loop on the other side and make these faster. Now, these models actually, the most recent thing we did, which is Mamba 2, was basically finding ways to reformulate even the SSM as something that can utilize matrix multiplications. And so now these models are actually have also gotten, I think, very fast. And now it's basically become a matter of implementation. So for example, and that can be very, very hardware dependent. So let me actually talk about kind of I'm going to skip this and just oops. So kind of well, yeah. So basically, we just kind of put out Mamba 2. Actually, Mamba 2 was done like 6 months ago, but me and Tree don't have time anymore, so it took a while to put on archive. But basically, we found a way to get it to leverage matrix multiplications, and it was optimized. Our first version was optimized on A100s, where it was getting, I think, still maybe slightly short of transformers, but it was getting quite good MFU and basically as fast as like flash attention for moderate sequence lengths of like a couple thousand. And then the longer your sequence length gets, then the linear time scaling of these SSMs kicks in. And for long sequences, it's much, much faster. However, basically, there's still a lot of room to be done there, but basically it's, there's definitely, there's a clear path forward where there's nothing fundamental, I think, stopping these from being really efficient too. And so a lot of it's just a matter of getting like really dedicated implementations to fit like the more modern GPUs like H100s and so on. And of course, I hope that now that these models are becoming a little bit more well known, that the hardware people will also kind of be thinking a little bit more about whether these alternate forms of models are also fundamental and whether they should be supported more directly. In fact, I've heard that Jensen seems to be quite positive on SSMs as well. So we'll see. So yeah, that's kind of another great question. Hopefully that sort of touched on some of the facets of it. Yeah.
Thanks.
Any more questions along those lines? How much time do we have left, by the way? I don't have the time available.
Maybe we can go past 7 p.m. Maybe we have 7 more minutes. I don't know how much you need. We can push it out.
I mean, you know, I have as much stuff to talk about as people are interested in, but I see we're basically out of time. So let me just see what is the last thing to mention. So the last thing I was going to mention is just to distinguish between the different types of SSMs. The previous version I showed was just like the basic SSM. And there I mentioned that these A, B, C, D were learnable parameters. Basically the only change, and so these are like, I call these all structured SSMs, which is like what S4 is. The only change from Mamba is that to make these parameters actually functions of the input instead. So instead of being like constant parameters, we'll make them some projection of the input. And that is, yeah, that's actually just it. And so this one changed. There's a bunch of motivations for it, but that's basically the change from S4 to Mamba. And that makes it work really well on language data. So final thing I'll kind of mention is that people think that, like, say, transformers are kind of useful everywhere. Actually, I think that we found that they don't work on everything, and there is still no free lunch depending on the type of data. And basically, you can think of data as being kind of more discrete or more continuous, which is also related to how compressible they are. So like text data is very information dense. You've kind of really, like, every text token has kind of a clear meaning. And to understand things, you might need to like really process like every single part of the text. And then more continuous data like audio and images are information sparse in the sense that they're very compressible, because your audio signal is like very smooth and continuous, and that means it's compressible. And these different forms of models work on different types of data. So the first type of SSM I showed you, which is like the S4 flavor and many downstream variants, are still really good at, they're much better at processing things like raw pixels, raw audio, waveforms, and so on. And then transformers and Mamba are much better at processing things like text and so on. And so you do kind of have to pick and choose where you want to apply the models. So yeah, I think that's just one thing I wanted to mention, because I think people, I think that's kind of more of an interesting intuition about how to think about them. And I think a lot of people don't have I think a lot of people know, but it's not really been like kind of formalized in a lot of places. So I'm gonna skip kind of the other experiments. I think you can find a lot of the Mamba results from the papers and so on. And so we wanted to kind of show more like most modern applications, like some more of the real-time stuff, and probably we're going to start seeing SSMs use larger language models. Maybe we'll see kind of like streaming video models and stuff like that soon, and so on. So yeah, we really are excited, and we think that they are kind of a fundamental type of model, which hopefully I've done some job of convincing you of. But I think there's a lot more work to be done and a lot more to understand here. So yeah, I think any final questions?
Thanks, Albert. Maybe a quick question on my side, and then we can pick up a couple from the chat. If you can share, of course, like what is the scale of the models that we saw in the demo you showed us roughly? Are we talking like a couple of billions or tens of billions, or like where are you pushing these in terms of scale? I think I saw something from one Chinese company where they pushed SSMs to like 20-something billion parameter, but like how do you think about the scale compared to transformers right now? You said there's no fundamental limitation, but yeah.
Yes, that's right. So basically, it's just a matter of people being willing to invest the resources. So I have seen basically these scale to kind of the lots of people have started doing it at like the 7-8 billion scale, which is kind of the first scale that kind of where the models are actually like interesting and matters. There have been kind of some larger models like mixture of experts models and so on that have been at like the maybe 20 to 50 billion scale. And I expect we're going to start seeing some more of these at a larger scale. I think basically it's just a matter of more people like verifying that these things work at say like 7 to 20 billion, and then it's just a matter of scaling it up and shoving in more data. Like I think there's kind of this folklore knowledge that around the 7 billion scale is where things that might work at smaller scale no longer work at 7 billion, and people have found that these models, especially like I mentioned, the hybrid ones, do seem very good at larger scale. So hopefully we're just going to start seeing more and more of these be scaled up. There's also kind of one research direction I'm interested in is kind of how to apply the existing transformer models to bootstrap new state space models. And so some ideas for like towards like distillation, kind of, and like ways of, I mentioned that these models are broadly related to attention as well. And there's some techniques that we can do to basically take a pre-trained transformer and try to convert it into a stasis model of a comparable size and comparable performance. So it's kind of another area of research, and hopefully you'll see some stuff coming from some of my students relatively soon.
Super cool. David asked, can you comment a little on the expressivity drawback of the Mamba 2 restriction on A?
Yeah, so unfortunately I didn't get into a lot of the details about Mamba 2, but I actually, let me briefly also just share my window here. So I talk about this a little bit in the blog post that we wrote on Mamba 2. I would recommend checking this out. I have a website for my group, and we talk. I think I mentioned a little bit about the restriction on Mamba 2 is a little bit. It's related to Mamba. But that's a little bit more restricted. I think the jury is still out on. Let me stop sharing. Well, okay, I forgot where it is, but the jury is still out on whether or not it hurts us or not. I suspect it doesn't really. And basically what happens in Mamba 2 is that we kind of tie some parameters in a way such that those recurrent dynamics we saw are going to be kind of more limited in a sense, or they're going to be kind of weight tied in a sense. So it's going to be like you have a large state, and instead of every part of the state being independently evolving through time, they're now kind of going to be evolving together in a sense. And I don't really think that's going to be an issue, because especially as we scale these models, we're going to be getting these massive states, and you will still be like scaling up the amount of different recurrences, or the the expressivity of the dynamics are still going to scale. It's just going to be like a little bit of a constant different than a Mamba 1. And I think there's also some intuition to indicate that that form of restriction might actually help. So another thing we kind of saw is that one of the most interesting results is that I mentioned earlier that these models struggle a bit on synthetic kind of synthetic recall tasks, and there's kind of this established benchmark on recall that has become popular, where we surprisingly found that Mamba 2 is so I don't have time to unpack this, but on some sort of recall task, Mamba 2 is way better than Mamba 1, and even it seems like, I'm a little surprised by this, but it was better than intention here. And this is not just a matter of like the new architecture and so on, or we haven't quite dug in, but I sort of suspect it might be related to the fact that this change in parameterization Mamba 2 that ostensibly is less expressive, but actually that form of restriction can actually be a helpful inductive bias for like this sort of like recall task. Yeah, so sorry, that was another kind of long-winded answer, but hopefully that points to some hints there.
Thanks. By the way, it's interesting to me you mentioned the 7B threshold, and I know that Tim Detmer's work was probably the first one that showed to me, at least, that the appearance of these outlier features is what kind of causes that phase shift, and then you cannot really extrapolate the research from sub 7B to above 7B. And so I'm curious, did you notice the exact same threshold for SSMs? Is there anything fundamental about 7B, or is this just like something that empirically turns out to be the case? Because I would suspect, I would expect that SSMs have at least a little bit different threshold than transformers. But then again, I
think you might be right. I think this is one of the really interesting things that I don't know either. Like because we don't have the resources or manpower to really like redo all the scaling laws. There's this question which is like, for Mamba, we've basically been adhering to the same recipes as transformers, like all the same hyperparameters, the same scaling laws, all these things. And it's been reasonably good for that. But there's a question of like, maybe actually there's a completely different local optimum. Like transformers have really evolved in tandem with like all sorts of the training process, right? Another interesting part is like the tokenizer. I actually think that when we start moving toward multimodal data and like data that's been less optimized for transformers, such as like one example is audio, but also like other forms of multimodal data, other forms of like maybe like code data or like byte level data. There's some evidence that people have found that show that like SSMs are actually better there. And so it's kind of this idea that once you break out of this like very tightly integrated ecosystem for transformers, maybe then these other types of models actually are like, I think they are fundamental, and people have found that out of the box, they might work better in other settings. I didn't mention another example is like DNA. Again, you can think of it as sort of like language, but tokenized differently. All of a sudden, these SSMs are just better out of the box. And so just to get back to your question, I don't know whether the same phase transitions happen, whether the same sort of laws apply to SSMs as transformers. I think that's for hopefully the community to be interested in figure out. Also, Tim Detmers is going to come to see me, is joining my department next year. So hopefully we might work together on investigating these empirically as well. We'll see. I'm very interested in all of these sort of questions.
Super cool. Okay, I see we are 10 minutes past. Maybe we can wrap it up. If you have some more time, there's a couple more questions from the chat.
Yeah, I'm happy to continue taking questions. I guess you can cut things off for your video however you feel appropriate. But yeah, I'm happy to stay on the call and kind of answer more questions.